Hello. I have to start with an explanation. A doctor friend suggested that in this era, a beard is not appropriate. New guy, what do you think? Doesn't matter. But we're not here to talk about partial facial here. We're here to talk about partial fractions. And the reaction to people in my calculus course right now would be, wait a second, we did that a long time ago. Why are we going back to talking about partial fractions again? When we do that? The real topic that you might be expecting right now would be to talk about something about series, and in particular telescoping series. And partial fractions are the technique that we use for telescoping series. That's almost reason enough to do it. Partial fractions keep coming up. This is one of those topics that keeps coming back and keeps coming back, and there's a little surprise at the end about what partial fractions tells you that can be applied to many, many more ways of exploring models and functions and differential equations and whatever. So let me give you a quick reminder about the partial fractions technique. So what you have is a fraction and something in the denominator, something in the numerator, and the numerator has been factored. You might have to factor it. But this is really not a very useful form for a lot of things. So what you do is you say, well, wait a second. I know another function that has the same asymptotes. And so, especially if you wait for the ink to dry. So this one has asymptotes at 0 and 2. This one has asymptotes at 0 and 2. And so at least you're in the ballpark. So then you split this up and recombine it. And I'm not going to bother with the bottom because that stays the same. But on top, in this case, you gather up the n terms and the constant terms, and you get something like this. And these are supposed to be equal. So that means that minus 2a is 3, and a plus b is 0. There's no n on this side, so there's no n over here. So b is the opposite of a is minus 3 halves, so there you go. I'll write that down. And so there we go. I'm going to take the 3 halves out to emphasize something, and I'm going to change the order so that we don't have a leading minus sign. Okay, so I can take this, which I'm sorry got to be hard to read, and I can rewrite it this way, and now we can do all kinds of things with it. One thing that we can do straight away, just as kind of a reminder, is to integrate. So if I want to look at the integral of 3dx over x minus 2. It doesn't matter what you call the integration variable, but people seem to like x, so I'm going to just play along. We can immediately apply that partial fractions expansion, and so this is 3 halves integral dx over x minus 2 minus 3 halves the integral of dx over x. And what's happened here is that this thing with the quadratic on the bottom is now 2 simple linear factors. That means those are logarithms, and so we can just continue on out. And what we have is I'm using the logarithm laws to combine them, and then it actually, because we want to apply the Archimedes limit, if we wanted to have an improper integral here, this is 3 halves natural log of 1 minus 2 over x. So this actually tells you right here that the improper integral, blah, 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 to infinity here would converge because you'd end up with the term that goes to infinity as you're taking the limit, that would be with x being very large, is essentially 0. And so all that matters is what happens at the beginning. Okay, we can also do this with sums. Make a note here, convergent integral. That means the sum is going to converge. Converging and knowing the sum are different things. This is a case where we can actually know the sum. So if we wanted to take the sum, same thing. that becomes 3/2 the sum of something a little bit more complicated, 1 over n minus 2 minus 1 over n. Now, wait a second. Sum, you have to specify sum from where to where. We can't start at 2. This can only start at 3. So let's start this at 3. And we can see what, first of all, we know this converges by the integral test. But we can see what's going on by writing out a few terms, and it's really kind of interesting. Don't forget the 3/2. And then things, I'm going to write them in kind of a wacky way. We're going to start with n equals 3. So that gives us a 1 over 1 minus a 1 over 3. And then the next term is when n equals 2, so we'll get a 1/2 and a 1/4. And then I'm going to start being funky. One thing here, don't simplify this. This is 1 over 1. It is not 1, it is 1 over 1. And a lot of times if you do that simplification, you'll miss the pattern, so don't. Okay. Now, to continue on, I'm going to write the next term with a little bit of an offset. So that starts with a 1/3 minus a 1/5. And I put it in a funny place, and what I want to emphasize is you've got minus a 1/3 plus a 1/3. Cancel. Gone. So keep that in mind. And then the next term will be, well, it always has been, a 1/4 minus a 1/6. And again, on the first line, I've got minus a 1/4. On the next line, I've got plus a 1/4. They cancel. So, and what's going to happen here is that everything, we get a dot, dot, dot at the end. Everything's going to cancel except for, well, we have the 3/2 still. And the 1 over 1, that didn't cancel, and the 1 over 2 didn't cancel. Everything else is going to cancel, and so in the limit, you just get 3/2 times 3/2. Interesting. Okay. So this is not there. Great. So this is what's going on with this telescoping series. You get the plus a 1/3 minus a 1/3 plus a 1/4 minus a 1/4 plus a 1/5 minus a 1/5, so forth and so on. It all goes like a pirate's telescope eye. So one quick thing, and I'm not going to go into the details. I just want to look at the partial fractions expansion of something slightly different, which is I want to change the denominator. I'm sorry, I want to change the numerator. So instead of having a constant, I have n plus 1. So this is fine. With practice, which I hope you're doing, if you want to look at the integral, and I'm just going to use n just to be pedantic because it doesn't matter what you name this variable, dn. This you can compare with 1 over n. This diverges. So we're expecting if we make a series out of this, that series diverges. Well, we know that that's the case. And so diverge, diverge. That's important. They both diverge. Let me just write down the partial fractions decomposition for n plus 1 over n times n minus 2. And it is, somewhere on this page, it is 3/2 times 1 over n minus 2 minus 1/2 times 1 over n. So what's going to happen here is if you integrate this, you're going to get a log of n squared or log of x squared, depending on your perspective. And so there's a situation. The telescoping won't happen because the positive terms and the negative terms come up with different coefficients. 1 is 3 and 1 is 1. So the negative 1 has a 1, but then you're going to add 3 times as much. So no telescoping. But there's something else, and that's the big deal about partial fractions here. This is telling you that somehow the 1 over n minus 2 term is 3 times more important than the 1 over n term. It's multiplied by 3. This one's only multiplied by 1. And what happens is when you start to look at power series and other kinds of expansions of functions as occurs in applications, you want to look for the big coefficients. Partial fractions is the first way to tell you which of these asymptotes is more important, and that will continue to be something to look for through the rest of doing applications with mathematics.